Hello everyone, hopefully you're doing well. In this video, we're going to take a look on the chapter 8, exponential astonishment. So, world population is currently growing by about 8 million people per year. At some point, it's really by the last report in 2023. So enough, if you said 80, I mean, sorry, 80 millions of people per year. So if you take the same rate and it would take only 4 years to populate the entire United States. The United States about 332 millions of people, but if world populations grow by 8 80 millions per year, then that will take only 4 years to populate the United States. So a growing population means new challenges of our species, which we can meet only if we understand this growth. So that's what we're gonna see in this chapter. We will investigate the mathematical laws of growth, especially exponential growth. So you said growth, but it's exponential growth, linear growths. We will focus on what we will call exponential astonishment, which is the intuition defying reality of exponential growth. Although we will emphasize population growth, we will also study many important topics that include the decay of waste from nuclear power plants, the depletion of natural resources, and also the environmental effects of acid rain. So, in the first section, Unit 8A, we will focus on the linear growth and exponential growth. So we're going to use an examples very quick. We said linear growth occurs when a quantity grows by the same absolute amount each year in each unit of time. But exponential growth occurs when a quantity grows by the same relative amount, that is, by the same percentage in each unit of growth. So I'm going to try to use an example to illustrate. But let's suppose that you have two towns. As you can see in this example, these two towns, one of the towns is called Street Town, and the other town is called Power Town. Now, imagine these two communities, Street Town and Power Town, each with the initial population. Let's say for the initial population for each of them, initial population. Let's suppose the initial population for each of them is 10,000 people, right? 10,000, right? So initial population here also is 10,000, right? Now, suppose the first one, say town, grows at a constant rate of 500 people per year. Grows at a constant, constant rate. That means the same thing of 500 people per year, right? I'm gonna try to move this to the other side, so just make sure we can understand it better. Okay. Now, if you look at on the left, I mean, the initial rate also here is 10,000 people. But we already say initial rate, initial population is 10,000 from both sides. But for Straight Town, every single year you add 500 people to that population. So after 3 years, how many people you think after year one, after year one, you know you have 10,000 plus 5. That would give you 10,500, right? After year two, that's year one. Year two, 10, another 5,000, that make it 11,000, right? After year three, it would make it 11,500. After year four, etc. So after every year, if you add five hundred, it's gonna uh goes by 500, right? But suppose on the other side for Power Town, instead of adding 500 people every year, I mean, it's go by 500 people. I mean, this population grows at a constant rate of 5%. So grows at 5% per year. Now, look, all you need to do, what is 5% of 10,000? So you know 10,000 plus 5% of 10,000 is 500. So we know after year one, you're gonna have 10,500. But after this first year, you no longer, the constant growth rate is no longer 500 because you remember it's 5% of the previous one. So instead of taking 5% of 10,000, now you're going to take 5% of 10,500, right? So you know for now, 5% of 10,500, it's gonna be a new number, right? So we know that would be something like if I go with a calculator, it's gonna be 525, right? So now year two, we no longer have year two is gonna be 11,000, 25 and etc. So now, if you take again, after year three, 5% of 11,025, year three, when you add 5% to this number again, it's gonna give you 551. 5% of 11,025 is 551. So, after year three, it's gonna be 11,576. Now, if you compare year three of both sides, you see if you add a number every year, constant number every year, that's what changes. You see, year three is only 11,500, but if you add 5% every year, it's cumulative, it's compounded. So it will be 11,576. At first, you can say, well, that's not really significant, You can even say that, like you can say it's really small, but it gets larger with each year passing. That's very important. That's why we show you this graph. If you do it over 40 years or 50 years, what is the big difference would be between Power Town and after like 40 something years, you see that Power Town would be like 80,000, right? Would be 80,000 people. But after the same amount of year, you would see it would be about 30,000 for Street Town. So Street Town and Power Town illustrate really the two fundamental different types of growth. That's why we said Town grows by the same absolute amount of 500 people each year, which is characteristic of linear growth because grows when a quantity grows by the same absolute amount in each unit of time. But you see the other one, Power Town grows by the same relative amount, but 5% each year, which is characteristic of exponential growth. So exponential growth occurs when a quantity grows by the same relative amount, that is by the same percentage in each unit of time. So the term linear and exponential can also be applied to quantities that decrease with time. Linear decay means that a quantity decreases by the same absolute amount in each unit of time. And exponential decay means that a quantity decrease by the same relative or percentage amount in each unit of time. So it all depends of what you do. We're gonna illustrate very quick with an examples, maybe one or two examples, not only one examples. So in this particular examples, we're gonna just go ahead and check. We said that state whether the growth or decay is linear or exponential. Remember, exponential is about relative percentage, like relative increase, so it's or decrease. So it's a percentages, right? You add percentages, but the other one you increase or decrease a constant number. So let's go with the first example so far. We said that the population of Meadowview is increasing at a rate of 300 people per year. If the population is 2,400 today, what would it take? What would it be in 4 years? Now, remember, it's increasing. It's increasing. If you add 300 people per year, right? So 300 people per year is 200, 2,400, the initial population plus after 4 years is four times 300. So you can do it this way. That's give you 2,400 plus four times so is 1,200. So that would give you a total of for A, okay? For A, it would be the 3,600 in, or if you want, you can just go ahead like A, you can do, oh, you know what? You start with uh, 2,400. If you add 300 to it on the first year, that give you 24, 27, right? 2,700. If you add another 300, that give you 3,000 after 2 years. If you add another 300, 3,300 after 3 years. If you add another 300, it gives you 3,600. If you want to do it this way also, remember this is year one, year two, year three, and year four. But the examples I show you make it much easier to go. But after 4 years, you have 3,600. Now, usually what I do, I go one examples and I let you do whatever we have left. If we go with B, remember in B, we said the population of Weinsberg is increasing at a rate of 10% per year. So do you consider this one, if the population is 10,000 today, what will be the population in 3 years? Now, one thing you can do, okay, one thing you can do, we have some techniques on how to do it every year, or we can just go ahead and do it year by year. Now, you agree for A, it is linear because we add the same absolute value. But how about B? Would that be exponential or linear? Yes, B would be exponential growth because it's in percentages. Now, there are different ways of doing it, either because they ask you if the population is 10,000 today, which is your initial, not 10,000, 100,000 today. If you add, what would it be in 3 years? You can take 10% of this on the first year, you add it. All right. So we have different ways of doing it. But you know what? Suppose you go 10% of every year. So you can try to do that also. Probably it would work. You can take the populations. Okay. So for year one, I'm gonna say year one, you take 10% of 100,000. So if you take 100,000, you multiply it by 10%. 10% means 0.1. Okay, so you take 100,000 times zero point 0.1. That's 10,000 people, right? So that's 10,000 Now, for year one, it would be 100,000 plus 10,000. That give you one, plus 100,000. So that would be 110,000. Right? Now, second year, you no longer take 10% of 100,000, you take 10% of 1,100. So if you take 10%, if you have 110,000 times point 0.1, so that gives you 11,000. So 10% of 110 is 1,100. Now, year two would be 110,000 plus 11,000. Okay. So when you add these two, it gives you 121,000. That's after year two. If you want to do 10% of 121,000, of course, remember you multiply by zero point 0.1, that gives you 12,100. Now, for year three, you're gonna have year three, you have 121,000 plus 12,100. Okay. When you add these two, okay, it gives you 1,000, 131,000, 133,100. So that's exponential growth. That's the first way to do it. I'm gonna erase all of this just to show you. If you want to pause the video, feel free, but I'm gonna show you a better way to do it by using formulas. Okay, so one of the techniques you can use to do that, if you want to know what would be this population in the future population that grow at a rate, you can take the population you have today. All right. If you take the population you have today, okay, and then you add, okay, sorry, you do the population you have today times plus one times the rate power t. So this is the time. So that's what give you, for example, let's say, for example, you know in percentages, in decimal. The R is in decimal, that's the rate of growth. So you know the population would be 10,000, 100,000. Sorry. 1 plus 10% is 0.1. Is 3 years. So you can say you have 100,000 times 1.1 power 3. So I bet when you do it in your calculator, the answer would still be the same. We're going to be 133,100 after 3 years for an exponential growth. So using these two examples, I'm pretty sure you can do any other examples, in this one. So feel free to let me know what you think, and we can continue doing some of these examples. All right. So use these two examples because the second one I do here is B. Usually I do one or two examples, then you can follow to do others. If you try let's suppose if you want to try E as an Edward, we said that for that particular example, the value of your house is increasing by $2,000 per year. If it's worth $100,000 today, what would it be worth in 5 years? Again, that's something very important. If you take E, Remember, today it's worth $100,000. Now, it's increased by $2,000 per year. So it's plus $2,000 for the first year. Because you said 5 years, you need to multiply by five. So that's give you 10,000, $100,000. Five times 2,000 give you 10,000, right? That would be five times two give you 10,000. So it would be $110,000 after 5 years. Okay, so I try to go with some of these examples with you, but feel free to do some other ones because that's what we're planning on doing for the rest of these sections. If we go with use the chessboard, I think we said use the chessboard a parable presented in the text. Assume that each grain of wheat weighs 1 out of 7,000 pounds. So they give us some measurements already. We can use the chessboard, but before we get there, our goal is really to because when they said how many grains of wheat should be placed on a square on square 16 of the chessboard, that's not just some works we need to find the total number of grains and the total weight at this point. So what I'm really suggesting you to do in this case, because we have so many different theory that we can do. This one, it's all about the impact of doubling. So we're gonna talk about before we even go over these examples, I'm going to introduce what we call impacts of doubling. So I'm gonna put it before this one. So we call it impacts, the impact of doublings, right? So I'm hoping you look at. So if we look at this graph, the graph, this graph, look at graph of Power Taiwan's populations, right? After 14 years, if you look at 14 years, after 14 years, the original population has doubled to 20,000, right? So we're talking about the pink curve. So the power, after 14 years is double, right? So in the next 14 years, it doubles again to 40,000. So you see, every 14 years, it's kind of doubles, right? I mean, 20 doubles to 40, 40 doubles to 80,000. So we have an idea because 42 years is doubled, again from 20 to or from 40 to 80,000. So if you look at this graph, right? So this type of repeat doubling in which each doubling occurs in the same amount of time is a hallmark of exponential growth, right? So there is a name for each of these when we talked about them that way, all right? So the time it takes for each doubling depends on the rate of the exponential growth, right? So that's very important to see. We'll see how, we can show you how doubling time depends on the percentage growth rates, right? So there are some parables, we're gonna say three parables we explore in this chapter that show how doublings makes exponential growth so different from linear growth. So I wanted to show you this, so how often you get the first doubling, the second doubling, the third doubling, but for the exponential growth, not the linear growth. The linear growth is just a straight line. There is no curve. All right. So that's what I want to show you here. Um, let, if we talked about our uh, uh, parable, because as we said, we have plenty of them, but it seems like the examples we want to cover in this is the chessboard parable. Legend has it that when chess was invented, in ancient times, a king was so enchanted that he said to the inventor, name your reward. Okay, yeah, we're talking about in this case, we're talking about the you know, the chessboard parable. So if we go with one chessboard parable, all right, parable. So chessboard parable, as we said, that's about legends, right? When chessboard was invented in ancient times, a king was so enchanted that he said to the inventor, name your rewards. If you please, king, that's the answer. If you please, king, put 1 grain of wheat on the first square of my chessboard, said the inventor. Then place 2 grains of wheat on the second square, 4 grains of wheat on the third square. I remember, so it's talking about the grains. So on the chessboard, I don't know if you understand it, but taking the chessboard, what he asked, please put 1 grain of wheat on this first square of my chessboard, 2 grains of wheat on the second square, 4 grains on the third square, 8 grains on the fourth square, and so on, right? So the king gladly agreed, thanking the man a fool for asking few for a few grains of wheat when he could have had gold or jewels. But let's see how it's add up for the 64 square board. So, 64 square boards, that's gonna be a lot. Remember, in the first square, if you take this square, so in the first square, he said only add 1 grain. So, grains on the square. Okay. Yeah, I write terribly terrible, right? It's really terrible the way I write it. So we're gonna go square. The second column would be grains on the square. Now, if when he put one, it's like one is equal 2 power 0, right? Now he said, then place 2 grains on the second square. So second square, he said put 2 grain in it, so 2 power 1. In the third square, fourth square, I think he said third square, uh, you know, uh, uh, 4 grains. So place 4 on it. 4 equal 2 power 2, right? You see how we're gonna put them in the fifth square, I mean fourth square, that would be 8 equal 2 power 3. You see how it's put it? 5, it would be 16 2 power 4. So if you continue that way, doing, as you can see, the exponent is n-1 because when we are in 5, you do 2 power 4. So for us, it's like if you do 6, you're gonna do 32 would be 2 power 5 because we're going to remove one. Now, if you go all the way down to the 64 square on the chessboard, it's gonna give you a number that is 2 power 63. Please, I would like you to look on your tables and you would see how much it's gonna be. So that would be a formula for us. At some point, we're gonna have a formula like 2n-1, right? That's what we're gonna have at the end. Now, what we said is like the king gladly agreed, thanking the man a fool for asking for a few grains of wheat when he could ask for gold or jewelries. But let's see how it's add up. You know, when I mean this table, I can show you each square gets twice as many grains as the previous one, right? So the number of grains on any square is a power of 2. The third column, if we add a third column that we don't see here, we could put the total grains. That's exactly those total grains you can see here. If you add one, uh, you know, uh, for all of this. So if we use the same type, at some point, what happened, you can try to find the parabola and parables and read it yourself on maybe on Google or something. Not only would it be impossible to fit so many grants on a chessboard, but this number is larger than the total number of grants of wheat harvested in all human history. The king never finished paying the inventor, and according to legend, instead of that, he was beheaded. So that's one of these, types of parables we use when we try to explain this. But in these examples, I might have my video too long for this, but we're gonna try anyway. In this one, it says how many, for these examples, we said how many grains of which should be placed on the 16 square? You know that already. I said for A, say we have a formula 2 power n minus 1. Also, if n is 16, so the number of grains you need to add is 16 minus 1 is 2 power 15. So if you do 2 power 15, then it would be 2 power 15 using your calculator, 32,000 grains, right? 32,000 768 grains placed on the 16 square. So the total of grains would be, at some point, there is the other formula that we can do is 206 power 6 minus 1 because that's the second formula we need to use. Of course, when we do these examples, that's very important. From the patterns, we see that the grain total for all 64 squares, we're gonna set it is 2 power n minus 1 all the way down there. So we're not gonna do it this way. So we're gonna keep this formula as is. So remember, use this formula. So 2 power 16 minus 1 would give you 65,535. All right. So we said 32,768 grains placed on the 16 square. So the total number of grains, would be is the total number of grains. All right, or of the total number of grains would be this one. And it would weight, because we're talking about the weight. Remember, use a chessboard, assume that each grain weight 1 out of 7. So if you have this, how much is gonna weight? Remember, 65,535 times 1 over 7,000 pounds, of course. How much it would weigh? It would weigh 9.36 pounds. Okay, it would weigh 9.36 pounds. So that's the examples. We have so many of these. That was only A. If you wanna do B, let's go B. I'm gonna try to do it very small and very quick. For B, it says that how many grains of which should be placed on 32 square, and find the total number of grains and their weight. So now the second question is about 32. As we said, if you do 32, the first thing to remember is you do 2 power what again? N minus 1 would be 2 power 32 minus 1 is 2 power 31. If you do this one, power 31, look at the number you're going to have. 2 times 2, or it's billions. 2 billions, 147,483,648 grains. The place, I'm gonna write it down for you. So these grains placed on what? You place these grains on the 32nd square. So that's why you're gonna place on the 32nd. So the total number of grains would be, remember again, total number of grains, 2 power n minus 1, 2 power 32 minus 1. That gives you a big number again. That's 4 billions, 294 millions, 967,295. And what would be the weight? You know, if I try to move this a little bit higher than that, let's try it. I'm gonna try it, right? Okay. So weight would be, you take this number, 4 billions, 294,967,295 times 1 over 7,000. So what would be the weight? Yes, this weight is meaningful. Is 613,567 pounds. So that will be the way. So follow these instructions. This is one of the techniques for of the impacts of doubling. So one of them is parable one. So we talked a chessboard, from hero to headless in 64 easy steps. So chessboard. All right. The magic penny is another one probably we would talk about later. If you use the magic penny, because remember our goal, for this one, we talked about the chessboard, but again, if we want, the second one we can talk about as impact of doubling is number two, the magic penny parable. All right. So one lucky day, you meet a program who promised to give you fantastic wealth, but hands you only a penny before disappearing. You head home and place the penny under your pillow. The next morning, to your surprise, you find two pennies under your pillow. The following morning, you find four pennies, and the morning after, 8 pennies. You see, it's double each time. Apparently, the lab program gave you a magic penny. While you sleep, each magic penny turns into two magic pennies. So, you can see this very quick, on every time, day one is like for you, day zero, you didn't have anything because day one, I mean that's the day they give the pennies to you. That would be the amount. Of course, I'm gonna try to explain. So on day one, they give you 0.01. So that's 1 penny. So 2 power 0 would be 0.01. And next day, you'll see it's double. So you're gonna have 0.01 equal, I mean, it's not equal, it's times times 2 power 1. Now you got 2 pennies, right? And remember, every day it's double. So you see on day two, 0.01 times 2 power 2, that make it 4, right? It's double. That's make it 0.04, I mean 4 cents, right? In day three, Again, continue to double. So that's 2 power 3. So it gives you 0.08. Now, you see what happened after 4 days, for example, you're still doing the same thing, 2 power 4, that gives you 16 cents. Now, just imagine after 365 days, what you're gonna have 0.01 times 2 power 365. So you see how much money you're gonna have. So at day T, you're still gonna have 0.01 times 2 power t. So that would be the formulas. So you day one is the day you made the program, generalizing from the first 4 rows of the table, the amount under your pillow after t days, the amount would be t equal 0.01. I mean, that's the amount, not equal. The amount would be times 2 power t, right? As long as you know what day it is. So we can use this formula to figure out how long would it take. Would it be until you have fantastic wealth? So after 9 days, can you try 9 days? If you try 9 days, so after 9 days, meaning the amount you're gonna have 0.01 times 2 power 9, please. Can you try that? Yes, after 9 days, it's only $5. $5.12, which is barely enough to buy lunch because you want to be rich. But at the end of 1 month, so at 1 month, t equal 30 days, right? So you're gonna have 0.01 times 2 power 30, 2 power 30. What do you think this one is? Don't forget you can use your calculator to do it. After 30 days, look what happened. Only 30 days, you get 10 millions, 737,000, 418.24. You're after only 30 days, only 1 month, you're already a millionaire. That is, you would be a multimillionaire within 1 month. And you would need a much larger pillow, of course, because they are all cents, right? In fact, if your magic penny keeps doubling by the end of just 52 days, you're gonna have $1 trillion, because if you take 52 days, they're taking 0.01 times 2 power 52. That's give you $45 trillion, right? You can even have paid the US debt after, the whole US debt after 1 year. So that's very important, which is more than enough to pay of all the national debt of the US. So you can do that, right? So that's the second, because remember, our goal here is to show you what we can take. The times it takes for each doubling depends on the rate of exponential growth, as we said. So what we're trying to show you here is different ways of doubling. All right. Now, if we go with these examples we just did, we said use the magic penny parable present in the text. How much how much money would you have after 21 days? So if you take 21 days, you just take 0.01 times 2 power 21. If you do these examples, I'm gonna use my calculator to do it, hoping it would be not difficult. So it would take, all right, those are pennies, all right? Remember that those are pennies. So it would be 2 millions 0.97152 pennies. So if you multiply it by 0.01, so you know that would be no, no, so sorry. So we do the whole thing. So that's not pennies, those are dollars I'm gonna add. So that would be 20,971.52. All right, so that's what we're gonna have. after 21 days. So how many days would it elapse before you had a total of more than $1 billion? So you can do trial and error for this one if you want to, but if they ask you how many days it would take you to do that, you can try so many of these. How many days? First of all, if I know 0.01 times 2 power t I'm looking for, and I know I need to get 1 billions. Now you can find t using either your calculator, but at this point, I believe it would be only 37 days. So please feel free to try it on your own. But to get $1 billion is only 37 days. Um, it will be. So very important to check this and hoping you can do this one that way. The last one of the parabola we talking about, the bacteria in a bottle parabola, was developed at the University of Colorado by Professor Albert, who delivered more than 1,750 lectures on the lesson of exponential growth around the world, over 40 years. So these guys you really need to look for it if you're interested to know more about this, because for our third parabola we return to the topics explored in the chapter opening questions, very early, you know but because you haven't seen that lecture yet, I'm gonna just read some of this here for you. Suppose you place in a single bacterium in a bottle of at 11 a.m. It grows and at 11:01 divides into two bacteria. These two bacteria each grow and at 11:02 divide into four bacteria, which go again at 11:03 divide into eight bacteria, and so on. You can see the patterns. Suppose the bacteria continue to double every minute and the bottle is full at 11 p.m., the number of bacteria at this point must be 2 power 60 because they double every minute, right? 2 power 60. But the important fact is that we have a bacterial disaster on our hands because the bacteria have failed the battle. The entire bacterial colony is doomed. So, questions one, the disaster occurred because of the battle was completely full at right? At 12, sorry. Disaster is full because it was full. So when was the battle half full? So that was the questions you were supposed to ask yourself, it it's full at 11, right? At 12, sorry. It's also when it was half full. So that's the question about the half. So because it took 1 hour to fill the bottle, many people guess that it was half full at half hour, like 11:30, which is not true because the bacteria double in every minute. They must also have double during the last minute. Remember, it's double the last minute, which means the bottle went from being half to full during the final minute. That's when it's full, right? That is, the bottle was full, half full at 11:59 because at 11:59 it was half. Boop, it's double in only 1 minute. So that's something you need to bear in mind. We have plenty of questions we could ask that way. Imagine that you are mathematically sophisticated, the bacterium, and at 11:56, you recognize the impending disaster. You immediately drop the N and on your soapbox and warn that unless your fellow bacteria slow their growth that dramatically, the end is just 4 minutes away. Will anyone believe you? Because remember, it's full at 11, at 12. So 11:59 it was all still half. So those are plenty of things you could do. Now, because it's a long parabola, I would like you to go and review it on your own. But in the meantime, I'm gonna just go ahead and probably do one example for this. How many bacteria, using the bacteria parabola, yes, we can. If we use the bacteria parabola, how many bacteria are in the bottle at 11:50? What fraction of the bottle is full at that time? So if we go with that examples, because I'd like you to try one on your own anyway, because I put three of them or two, four of them. I don't know how many. But if we do the first examples here, we said that at 11:59, 50, at at 11:50, so there were, you know, 2 power 50. So according to what we just said here, at the battles, right? We said 2 power, remember, 60 minutes, 2 power 60, 50 minutes, 2 power 60, 50, right? So that gives you at some point such a big giant number. I believe that should give you 1.1 power 10 power 15. It's over trillions, right? Bacteria in the battle. The battle is full at 11, at 12 p.m., right? Remember, at from 11 a.m. to 12 p.m., it's full. So it was half full. Remember, half full at what time again we said? At 11:59 because it's double every time, right? And when was it was quarter full? Quarter before you make it half. Yes, it's a quarter full at 11:58. So if you want to know 1/8 of full, because if you take half again, 1/8 of full at what time? 11:57. And you can go so on and on. So if you continue in this manner, we find that the battle was, if we continue that way, 1 out of 1024 full at 11:50. So that's why you're gonna figure it out how much we had in that one at 11:50. So this could express, how would you express it? Because we can say it that way as 1 out of 2 power 10, right? Um, full at 11:50. I know that's quite a lot to explain this way, but it's one way of explaining everything. Now, all right. Something very important to see. We said key facts about exponential growth. We said exponential growth, doubling lessons. We went over the three parabol reveals, at least two key lessons about the repeated doublings that arise with exponential growth. Exponential growth leads to repeating doubling. With each doubling, the size of the most recent doubling is approximately equal to the sum of all preceding doublings. Exponential growth cannot continue indefinitely after only a relatively small number of doublings. Exponential growth quantities reach impossible proportions. So remember that you need to be careful with exponential growth. Very important facts about exponential growth. If we talk about doubling times versus initial amount, so that's another type of examples we can try to understand when we said doubling times or initial amount. We said, would you would you rather start? Because those are type of questions we can probably try to answer. We said, would you rather start with 1 penny and double your wealth every day, or start with 1 dime and double your wealth every 5 days? Assume you want to get rich in the long run. So, what do you prefer? Receive 1 dime every day, double it. I mean, you start with 1 dime and double it every day, or receive 10 dime, 10 cents, and you double it every 5 days. Which one would you prefer? You should take the penny. After only 5 days, the penny was reached. Remember, look, you should, if you take the penny, remember, penny for us, would reach, okay, at 2 power 5. That would be 32 cents, right? And that's A. But well, the dime has gone to only after 5 days, 10 times 5 is 20 cents, right? So you should definitely go with the penny. That's more simple. Would you rather start 1 penny and double your wealth every day, or start with $1,000 and double your wealth every 2 days? Again, here, the penny would grow, remember, uh, 2 power n cents, right? So n cents every day. But if you take $1,000, so it's gonna 100,000 cents. Since it's double only every 2 days, it would grow at a very big number, right? After experimenting with various values of n, you would find out that the penny has gone to a balance larger than $10,000 in just 34 days. So at this point, it would be better that you go again with the penny for B. Okay, so hopefully this one happened. You can use it to do more examples. So in a different video, we're going to come back for section unit 8B, doubling time and half time. Take care. I'll see you in a different video.